Hello and welcome to this episode of Math with Martinez. We are in our Pre-Cal Unit 5, Exponential and Logarithmic Functions. And in this video, our goal is to be able to graph logarithmic functions and analyze key features such as domain, range, zeros, asymptotes in behavior, and intervals over which the function is increasing or decreasing. So I want to start by just highlighting this really important key concept. A logarithmic function, recall, is the inverse of an exponential function. It is the inverse of an exponential function. So using our graphing calculator, let's actually take a moment to sketch these two graphs. I've got my calculator here. We're going to begin by sketching the function just log base 10, so I don't need to write a base in there, but log of x. I know its base is 10, so they understood there. Let's look at our graph. So this is the shape of our graph. Your graphing calculator might do like mine and look like it actually stops going down, but that's just your calculator's inability to sketch perfectly. It does keep going down and down and down and approaching that vertical asymptote. It's crossing on the x-axis at 1. So when we sketch that out, our logarithmic function is going to cross right here at 1. It's going to be approaching that axis and then crossing right there. Okay, just like that. And the inverse of that, the inverse of log base 10 of x, is the exponential function whose base is 10 and it's raised to the x power. So when we look at that graph, there it is. It is crossing on the y-axis at 1, and on the left-hand side, the end behavior there is that it's approaching the asymptote. So that's going to look like, actually let me change this color just slightly here. Let's make this blue to match. And then we'll do this next one in red. So this one is going to cross here at 1. Like so. Oh my goodness. I don't know why it disappeared. Oh, that's not my best sketch. Let me try one more time. So sorry. There we go. That's a lot better. Okay. So what you should see here is that these two graphs are actually perfect reflections of one another. This was the point 0, 1, and over here we have the point 1, 0. This graph has an asymptote here. Its asymptote is at x equals 0. And this graph has an asymptote at y equals 0. The domain for this function is negative infinity to infinity. And the range for this function is going to be from 0 to infinity. Whereas for its inverse, the domain here is 0 to infinity, and the range is all real numbers, or negative infinity to infinity. So their behavior is that they really are just reversing each other. They are reflections of one another across that line y equals x, which is this line right here. This is the line y equals x. They just perfectly reflect each other across that line. So that's just something to keep in mind when we're trying to find key features of our functions, especially if what we know is the original function and we're trying to figure out something to be true about the inverse. So let's go ahead and look at a couple examples here. We're going to graph the function and identify its key characteristics. We're going to begin with log base 3 of x. We're going to follow those steps, and I'm going to split the view here so you can see the calculator, how this would be done. Because this first one, it was just a log with a common base of 10, which I have the key, the button there on the home screen to get log of base 10. But if we want log base 3, then what we want to do is go ahead and select the y equals on our graphing calculator so that we can graph. Then you're going to select math, and you're going to scroll down to option A, which says log base. Now you'll actually be able to type the base in the subscript box, which in our case is 3 here, and the x in your argument box. Make sure to choose the x next to the alpha key. That's your variable. Press enter, and now we're ready to go. All right, so there is our function. We can see that it is certainly crossing at 1, that we are going to have a vertical asymptote, which I'm sketching here, on my y-axis, so that's at x equals 0. And then if we go to the table, we'll be able to get some more nice, pretty points. So error in all those negative regions. Okay, at 9, I have 2. And that makes sense if you think about the inverse of that. 2 to the power of, 3 to the second power is 2. Oops. Okay, so now we sketch. And it's going to flatten off quite quickly here. There we go. And now we're ready to state these features. Our domain is everything on the right side of our asymptote, so that's going to be from 0 to infinity. The range is going to be all real numbers because it goes up and down forever. Our x-intercept is at when x is 1. Remember, for x-intercepts, the y value is always 0. Our asymptote is x equaling 0. This function is always increasing for all of its domains, so it's increasing from 0 to infinity, but it's never decreasing. And our end behavior is kind of unique here because, check this out, we have, as x approaches infinity, because one end of this graph is going to x values approaching infinity, your f of x will also keep approaching infinity. It is going to keep going up. Not very fast. If you look at your table here, the values don't increase very quickly, but they do keep going up. The only other thing here that's different is that it's not going to approach negative infinity for your x values on the other end. We actually are only approaching where our asymptote is, and that's as x approaches 0. And as x approaches 0, this function is approaching negative infinity. So that's one example of identifying key features for a logarithmic function. Let's do just a couple more here. This function is very similar, so we should be able to just come in here and edit it. Just going to delete this and insert a fraction, and that's the base, the fractional base of 1/3. So the base is 1/3. So if you're thinking like an exponential function, that was a decaying function. And so you'll see here, this logarithmic function does look to be decreasing, decaying as well. So that should be true because they are so connected with one another. We've got, I am drawing my asymptote here. This is at x equals 0. I can see that it goes through the point 1 on the x-axis, and it should be at 9 that it's down at -2. Yep. And just a little change, just a little edit from our last graph because it's decaying. Okay. The domain, once again, is from 0 to infinity. Your range is going to be from -infinity to infinity because it keeps going up and down forever. Your x-intercept, once again, for this graph, is going to be at 1, 0. That's where it crosses. Your asymptote is at x equals 0. But this graph is never increasing. It's decreasing for all of its domain, which is 0 to infinity. And our end behaviors. As x approaches infinity, the function graph is actually decreasing, so it's going down to -infinity. And as x approaches the other side, what is the x value that we're getting close to but not touching? 0. It's going up to infinity. All right. Oh my goodness, I didn't realize there was a +1 on this graph. Can we go ahead and just take that off? Delete that. Okay. So erase, white out, scratch off that +1 there. Now check and see what happens when we have this next example. Okay. Let me just clear this off. Remember, we go math, and it's option A down here, log, where we can edit our base. We're going to have in front a negative, so be aware of that. Negative, log whose base is 2, and then it is of x minus 2. Okay, so quite a bit has changed here. Let's see this graph. Now, ladies and gentlemen, when you go to the table, you'll see that everything 2 and smaller, there is going to be an error. And that's because our asymptote is now at 2, affected by the value that is being subtracted in here with your x. So when you have a value in there, that's going to cause that horizontal shift to the right. So now our asymptote is at x equals 2. And then we have the point 3, 0. And that is going to be your x-intercept. We have a nice point. 4 is at -1. And we also have at 6, it's down at -2, and at 10, it's down at -3. So the reason why this graph is opening down is because of the negative that is in front of our logarithm. That's why it is going to be decaying. So our domain is going to be adjusted as well because of the new location for our asymptote. It's going to be everything, stick with blue. It's going to be everything from 2 to infinity, but our range is still going to be all real numbers. That'll be true for all logarithmic functions. It'll always be that the range is all real numbers. Again, this graph is never increasing. It's going to be decreasing for all of the domain. So that means from 2 to infinity. And our end behavior, as x approaches infinity, this function is going to be approaching -infinity because over here, let me grab my tool so you guys can see. Over here, this is as x's are going to infinity, that's this direction, it's going down. So like you see there. And then in the other direction, As x is approaching our asymptote, which is where 2 is, the function is approaching infinity. So there you guys go. That is it for graphing logarithmic functions and identifying their key features. You're definitely able to use your graphing calculator to do that. You just have to remember how to get your log to have different bases. If you had any questions, please take a moment and share those now. And until next time, stay fired up.